Our next example is the elasticity system. So let omega contained in R3, so we are restricting ourselves to R3, be a bounded, open and connected set. This is the volume occupied by an elastic body. So this is omega, it's the volume occupied by a elastic body. So gamma equals d omega equals gamma 1 union gamma 2, where gamma 1 intersection gamma 2 is empty. Okay, so is gamma 0 intersection gamma 1. Okay, so we have a portion here. So this is a three-dimensional body. So this part we call as gamma 0 and this part of the boundary is gamma 1. Okay, now surface measure of gamma naught is strictly positive. Okay, that is assumed here because we are going to impose a Dirichlet condition there, and then nu equals unit outward normal on gamma. A body force F equals F1, F2, F3 acts on omega, and a surface force G equals G1, G2, G3 acts on gamma 1. Okay, so there is a force which acts on gamma 1, and then could be something like a shear force or something, and then you have a force which acts. So we want to study the deformation of the boundary. Okay, so let U equals U1, U2, U3 be the displacement vector. This is the one which we are interested in. So when you act this body on with these forces, we want to see how the body deforms. That means we have to compute U at every point of omega. Then we know. Now we have the strain tensor. We have seen this already in the context of Korn's inequality. So we have epsilon ij of U equals 1/2 of dui by dxj plus duj by dxi. This is a symmetric tensor. Okay, so 1 less than equal to ij less than equal to 3. Okay, now stress tensor is sigma ij, and this is the one of U ij equals 1 to 3, and this is the one which tells you how the body is going to deform under the action of the forces. So the balance of forces will be written in terms of this. Now we want to know what is the material the body is made of and how the stress and the strain are connected. So stress strain relationship depends on the material omega is made of, and it's called the constitutive law. In this case, we will assume that it's a linear law which we call as Hooke's law. So this is linear elasticity. So there is a linear relationship between the stress and the strain, which we will now write down. So we have sigma ij of U equals lambda times sigma k equals 1 to 3 epsilon kk of u times delta ij plus 2 mu epsilon ij of u. Okay, so lambda, mu are positive constants. These are called Lamé coefficients. And delta ij is the Kronecker symbol. So that's equal to 1 if I equals j and 0 if I is not equal to j. Okay, so this is the stress strain relationship. So lambda could be greater than or equal to 0 and mu strictly positive. These are called the Lamé coefficients. So the elasticity system is the following set of equations. Okay, minus of the divergence of sigma. So minus sigma j equal to 1 to 3 d by dxj sigma ij of u equals fi in omega I equals 1, 2, 3. So this is a set of 3 equations. So you have that d by dxj of sigma ij is this is the balance of forces. Okay, then u equal to 0 on gamma naught and sigma j equals 1 to 3. This is the natural boundary condition. Sigma ij of u nu j equal to gi on gamma 1 less than equal to I less than equal to 3. Okay, so this is the elasticity system. So H we will call H as Hooke's law and E as the elasticity system. Okay. So we want to write down a weak formulation. So we are, as we know from past experience, we are this is a second order equation and the system of equations. So we are going to work in product of H1 of omega, and also we have to put the condition u equals 0 on gamma naught. We have to impose it because that's the essential boundary condition, namely the Dirichlet boundary condition. So we define V equals set of all V in H1 of omega cubed such that V equal to 0 on gamma naught. So V would have 3 components, V1, V2 and V3. Okay. So we define A of uv for uv in V, we define A of uv is equal to sigma, integral on omega, sigma j equals 1 to 3, sigma ij of u, epsilon ij of V dx. Now we put in the Hooke's law. So by H, so what is Hooke's law? Sigma ij of u is lambda epsilon kk of u delta ij plus 2 mu epsilon ij of u. So 2 mu epsilon ij of u will give you here ij equal to 1 to 3, and therefore so the second term, so you will get integral on omega, so plus 2 mu epsilon ij of u epsilon ij of v dx, and the first term will give you epsilon I. Only when I equals j you will have delta ij is 1, and therefore so delta ij is 1 only if I equals j, so this term will not survive for any other ij, and therefore when I equals j, epsilon kk is nothing but So epsilon kk is duk by dxk plus duk by dxa power half, so into half, so that is equal to duk by dxk. Sigma over 1 to 3 will give you just divergence of u. So this will give you lambda divergence of u times divergence of v plus 2 mu sigma over ij equal to 1 to 3 of epsilon ij bu. So this form, so this implies that AUV is symmetric. The first form does not tell you, but the second form tells you that it is a symmetric bilinear form. So F in L2 of omega power 3 and G belong to L2 of gamma 1 power 3. Okay, so weak formulation, find u in V, so the trace is V such that A of uv equals integral omega f dot v dx plus integral over gamma 1 g dot v d sigma. Okay, so this is the weak formulation. So you have the linear form, you have the bilinear form which is symmetric, and therefore we want to know which is okay. So we want to know how we came to this. So we want to justify this weak formulation. So if u were a weak solution, smooth enough, we can recover E. How? So if V is also smooth enough, uv in V, so you have AUV equals integral on omega sigma ij of u, epsilon ij of V is 1/2 of du I by dxj plus duj by dxi. But sigma is symmetric. Stress tensor is always a symmetric tensor. So I don't know if I said it here. This is a symmetric tensor. Okay, so if you using that fact, this is, it's easy to check that. Okay, this is sigma ij equals 1 to 3, and that is equal to integral omega sigma ij equals 1 to 3 of sigma ij of u into dui by dxj. So the half will get absorbed. So sigma ij equals sigma ji. So these, there will be matching terms here repeated twice. Each term will be repeated twice of this kind, and so the half will go away, and therefore you will only get this dx. And that, if you use Green's theorem, this will be minus integral on omega sigma ij equals 1 to 3 d by dxj of sigma ij of u vi this is v here dx, and then the integral on the boundary on gamma naught v is 0, so you will only have integral on gamma 1 sigma ij of u and vi, and because we turned over the jth derivative, you have dj nu sigma. So now if you take v is in d omega cubed, then the boundary term will disappear, and therefore you will have, so the weak solution, call this W, W will imply that minus integral on omega sigma ij equals 1 to 3 d by dxj sigma ij of u vi dx equals integral f dot v over omega dx. There also there will be no boundary integral term. So now you successively take v in d omega and you take v equals v 0 0 or 0 v 0 or 0 0 v sub 1 by 1. So you will get that minus sigma ij equals 1 to 3 d by dxj of sigma iju equals fi in d prime omega. I equals 1 to 3. And then of course you have that u equal to 0 on gamma naught since u belongs to V. Okay, so we only have to look at the other boundary condition. So then of course you know that this can be made if everything is smooth enough, this relation in L2 as you can see from these equations here, and therefore going back to this equation here you will get sigma integral on gamma 1 sigma ij of u vi nu j d sigma equal to 0 for all v in V. Sorry, not equal to 0, equals integral on gamma 1 of gi dot v d sigma for every v in V, and from this you can easily go back and get that sigma ij of u nu j is equal to gi on gamma 1. Okay, so this is the so you can recover the original system by means of from the weak formulation. Okay, so now we want to study the existence and uniqueness of the weak solution. So we want to apply Lax-Milgram lemma. So we have to show that it is elliptic. So we now proceed to do that, and for that we first need a preliminary lemma. Let V equals V1, V2, V3 belong to capital V. Be such that epsilon ij of V equal to 0 for all 1 less than equal to ij less than equal to 3. Then V equal to 0. Okay. So proof. We have already seen again in the proof of the Korn's inequality that d2vi by dxi dxj dxk equals d by dxj epsilon ik of V plus d by dxk of epsilon jk of V ik, sorry. No, this will be ij minus d by dxi of epsilon jk of V. So since all the epsilons are 0, this implies that d2vi by dxi j dxk equal to 0. Now omega is connected, so all second derivative vanish, and therefore this means that V is linear. So Vi equals sigma ai plus sigma Bik xk. Since all the second derivative vanishes and omega is connected. So now, so ai, bi are all real numbers. Okay. So now you have that dvi by dxj plus dvj by dxi equal to 0, and therefore you have that bii equal to 0 for all I, and if I is not equal to j, bij plus bji equal to 0. So it's just algebra, you just plug it in here, differentiate these expressions, you will get this. So now you put set b12 equals minus b21 equals b1 equals minus b3, sorry, b23 equals minus b32 equals minus b1, and b31 equals minus b13 equals minus b2. Okay, and then a equals a1, a2, a3, and b equals b1, b2, b3, then you will get that v is nothing but a plus b cross x, where hat is the vector cross product. So you just have to check out these calculations. So this means that, so what does this, what do we actually prove? So when you have there is no strain in the thing, that means there is no deformation at all. So we are just moving the body rigidly, it's just a rigid translation, so rigid motion. Equals translation plus a rotation. That's exactly what each a is the translation part, b cross x vector product is the rotation part, and therefore if you have a deformation in which there is no strain, that means the deformation tensor is 0, then it has to be a rigid body motion. That's all we have shown. So v equals a plus b cross x, and now v equal to 0 on gamma naught. Measure of gamma naught is strictly positive, and this implies that v vanishes at least 3 non-collinear points and that will imply that v equal to 0. So if you put this equal to 0, then you will get you put this equal to 0 at 3 non-collinear points, then it will happen that v equal to 0. So that is just some linear algebra which you can check. Okay, so now that we have this lemma, we can now state the following theorem. The bilinear form A is V elliptic. So proof. So for V in V, what do we have? That norm V square is sigma I equals 1 to 3 norm Vi square 1 omega. Okay, so we need to show, there exists alpha positive such that for all V in V you have AVV is equal to alpha times norm V square. So if not, then for every however small an alpha you take, you will get a contradiction to this. That means there's a vector which is not supplying this one. So I can take alpha equals 1 by n, and I can also normalize V. We have done this kind of thing when there exists Vn in V such that norm Vn V equal to 1 and A Vn Vn is less than 1 by n, that is A Vn Vn goes to 0 as n tends to infinity. But what is A Vn Vn? If you look at AVV, it is the sum of two squares. One is divergence U V square plus epsilon ij V square. So this means that, this implies that epsilon ij Vn tends to 0 in L2 of omega for all 1 less than equal to ij less than equal to 3. So Vn is bounded in V, and omega is bounded. V is of course contained in h1 of omega cubed, and therefore relic Kondrasov implies there exists a subsequence nk such that V nk converges to some V in L2 of omega cubed, because it's bounded in h1 of omega cubed, and therefore it converges to some V in L2 of omega cubed. Now we also have Korn's inequality. What is Korn's inequality? Norm V square V is less than or equal to integral on omega sigma ij equals 1 to 3 mod epsilon ij V square plus integral omega sigma I equals 1 to 3 mod Vi square. This is Korn's inequality. Now epsilon ijv goes to 0, and this is convergent in L2. So this means that V and K is Cauchy in V, and this implies that V and K converges to V, in fact, in capital. So since it already converges in L2, so it will have to converge in V. But then epsilon ij of V equal to 0, this implies that V equal to 0, but then norm V and K square V equal to 1, and this is a contradiction. So we have a contradiction, and therefore you know that this is elliptic. Therefore A is elliptic implies there exists a unique weak solution by Lax-Milgram, and A is symmetric implies weak solution is the minimizer over V of the strain energy, or of the energy JV equals 1/2 of AVV, that is integral omega of sigma ij equals 1 to 3 sigma ij of V epsilon ij of V dx minus integral on omega f dot V dx minus integral gamma 1 g dot V d sigma. Okay, and this this is the energy of the system, and for equilibrium you need that it has to be minimized, and that is exactly called the principle of virtual work. Namely, the elasticity system solution is nothing but the minimizer of the energy. Okay, so this thing. So this is the existence, uniqueness, and the weak formulation for the system of elasticity.